Hemodynamics basics. What is the meaning of hemodynamics? Hemo means blood. Dynamics means study of the energies or forces of the movements. So the hemodynamics is the study of blood movement through the circulatory system. In this part, we'll study the blood, what are the components of the blood, what are the definitions and principles of hemodynamics, and we have the cardiac, arterial, and venous hemodynamics. Blood. What is the blood? Blood is composed of, it's a tissue, kind of tissue, but it's in the liquid form. So any tissue in the body, we have many tissues like stiff, hard, like bone, we have fleshy, and we have liquid. And the liquid tissue we have is the blood. Okay, the volume of blood in our body is around the 5-liter volume. Components of the blood, we have plasma and cells. Plasma are usually 58% of the whole volume, and the cells compose almost 40 to 45%. Come to the plasma. Plasma is mainly made of 90% almost, or a little higher than 90% of water. Other components called solids, and these are like plasma proteins, clotting factors, electrolytes, immunoglobulins, hormones, a lot of components. All of these gathered together are called the solids of the plasma. When you come to the cellular components, we know that they are 40 to 45%. And actually, there is a test that measures this called the hematocrit test. Hematocrit is one of the tests. We'll come to it in a moment. So what are these cells? We have the red cells. These are called erythrocytes. Okay, and they contain the hemoglobin that is important for the transport of oxygen. We have the white cells, named as leukocytes, and they are protecting, they are our soldiers, our defense. And we have the platelets and called thrombocytes. So thrombocytes are the platelets, and they are important for blood clotting. Now we come to the hematocrit, like as I mentioned earlier. Hematocrit is the measurement of the cellular component. So how much is the cells we mentioned earlier? They are almost 40 to 45. Usually 45, these are more in the males, and 40% are more in the females, right? And as you see here, this is a test is done through in the blood labs, and they take the blood and put it in a tube with some anticoagulant so that they can measure the blood as cells, not clotted blood. And as you see here, we have, let me put this one here. You see, this is the red blood cells, white blood cells, and here is the plasma. It's under the effect of a centrifuge, they can reach out to these layers. Now we come to the hematocrit, like as I mentioned earlier. Hematocrit is the measurement of the cellular component. So how much is the cells we mentioned earlier? They are almost 40 to 45. Usually 45, these are more in the males, and 40% are more in the females, right? And as you see here, this is a test is done through in the blood labs, and they take the blood and put it in a tube with some anticoagulant so that they can measure the blood as cells, not clotted blood. And as you see here, we have, let me put this one here. You see, this is the red blood cells, white blood cells, and here is the plasma. It's under the effect of a centrifuge, they can reach out to these layers. Now we come to an important point to discuss about the hemodynamics, which is the wording or the terminology. One word that is going to be used is the density. What is the density? Density is the weight or a mass of 1 unit volume. Usually a unit volume is cubic centimeter, which is an ml. This one, ml. And what is the weight? Usually we use the word gram or the unit gram. So grams per ml, this is the unit used for density. Okay, to make it easier to understand, if you have 1 cubic centimeter of water and 1 cubic centimeter of steel, put them both in a weighing scale. Of course, steel is a higher weight, although both are having the same volume. But steel is a higher weight. That's why we call steel as what? Steel is more dense than water. Density, of course, if you come to the blood, density of blood is higher than that of water. Density is expressed with the Greek letter called rho, this letter, rho. And rho is the universal letter given to the density in all physics specialties. Another word is the viscosity. Viscosity is the stickiness or the thickness of the fluid, okay? And we have more viscous, more sticky, it resists the flow. For example, you have if you have a syringe containing oil, another syringe containing alcohol, and push the plunger of each syringe, which one is having a higher resistance? Higher resistance goes to oil. So oil is more viscous, okay? So it is the resistance to the flow, is the stickiness between the particles, the bonding between the particles, right? And the unit is called POISE, P-O-I-S-E. And of course, the viscosity of blood is more than that of water because, again, of its components. Viscosity is giving the Greek letter eta. This is the eta, how it looks like eta. So we have density, rho, viscosity, eta, and this is the letter giving for viscosity. A third word is called the inertia. What is the inertia? Inertia is a resistance of any material or any component that we are discussing. Its resistance to change of its status or its current status or its current velocity. The velocity could be zero, meaning that this part is fixed in position, or it's moving, so its position is changing. And the change of position, we call it the movement, it has a velocity or a direction and speed. So if I say that this organ, or sorry, this particle is moving at this velocity, means that it has a direction and a speed. If I want to change the direction or change the speed, I have to exert some energy to do that change. So the resistance to change is called inertia. Okay. Velocity, again, as you mentioned, velocity is what? Velocity is a speed in a known direction. So swiftness or speed in a known direction, this is called the velocity. The units of velocity are the same as speed, which is how many centimeters per second, or how many meters per hour, or how many miles per hour. This is, for example, this is the speed in the use in the streets. So this is the unit of velocity is the same unit as speed. Velocity is the speed in a known direction. This is one of the things that we need to understand well. Another word in terminology of hemodynamics is the flow. It's giving this letter Q, Q quantity, okay? So flow means what? It's the volume flow. We are talking about volume. Volume means we have 3 dimensions, of course, you know that this is the volume, all right? So what is the volume flow rate, or the Q, is the volume of blood moving during a unit of time. What is the unit of time? Is usually we take 1 second as unit of time, all right? So if I'm having from point A to point B, how many mLs that moved in this unit of time between point A to point B? For example, I might have 1 ml. So this is the flow rate is 1 ml per second. Or I could have like 10 ml. So the flow rate here is higher, meaning that I have 10 mLs of blood are moving in 1 second from point A to point B. So this is the flow rate or the Q. All right. Again, the units are what? ml per second, liter per minute, means that a volume per unit of time. We have an equation that can help us to understand this flow rate, and it says that flow rate Q equal the mean velocity times cross-sectional area. This is the cross-sectional area, and this is the mean velocity of the blood. So if I'm having increase of the velocity, I will get higher Q. If I'm having wider area, I'm getting higher Q. So velocity increase, I'll get more Q. Area increase, I get more Q. Just a note here that the cross-sectional area, if you come to the surface area or any circle, if you want to get the area of it, these are the formula. We have area equals pi times r squared. R is the radius. Squared means multiplied by itself 2 times. So if I'm saying that pi means 3.14 multiplied by the radius, multiplied by the radius. So again, multiplied by the radius twice. To study more of the volume flow rate or the Q or the flow, okay, we have two factors we mentioned in the equation. We have the velocity and we have the area, the cross-sectional area. Now we study the effect of velocity over the flow and the effect of the cross-sectional area on the flow. Now, if I'm having this velocity, for example, I have a blood flow from in 1 second, it moves from here to here, meaning that the velocity is low. So from this point to this point, okay, this is the distance or the velocity taken in 1 second. Another one here, in 1 second, the velocity moved from here to here. So this is a higher velocity compared to the lower velocity. What happened to the Q? The Q here, or the volume flow, will be higher if I'm having a higher velocity, meaning that I can pour more blood if I'm having a higher velocity, assuming that we are having the same cross-sectional area. So here, the same cross-sectional area in two examples, but I'm having a higher velocity. Simple analogy. If you have the garden hose, you make the open more water, it comes out with a high velocity because it transports a higher volume. If you lower the faucet or lower the flow, you get less velocity because less velocity are associated with lower flow. So again, higher velocity, higher flow, lower velocity, lower flow. Lower velocity, lower flow, higher velocity, higher flow. Other thing is the effect of the cross-sectional area. A cross-sectional area and its effect on the flow or the volume, okay? Assuming that we have two garden hoses, one that is a small garden hose and another one that's wide, or assuming one garden hose and this is the fire hose, okay? So we have two hoses here. One is narrower cross-sectional area, the other one is wider cross-sectional area. What happened? Okay, assuming that we're having the same velocity of water flow in the garden hose and in the fire hose. Which one will deliver more water is the garden hose. Why? It has a wider cross-sectional area. The same story here comes when we have a narrow vessel and a wide vessel. Okay, lower cross-sectional area, we have lower volume flow, and wider cross-sectional area, we get a wider volume flow. So again, what are the factors? We have the velocity and we have the cross-sectional area. Now, as we finish the basic terminology that are used in hemodynamics, now let's study the forms of blood flow. Usually, blood is flowing in three patterns: pulsatile, phasic, and steady flow. So let's study first the pulsatile flow. Pulsatile flow is usually we see it in arteries and it's related to the cardiac cycle. So pulsatile flow, usually you can see it in arteries, and it is related mainly to the cardiac cycle. Cardiac cycle has what? What is the cardiac cycle? We have systole and we have diastole. Systole and diastole mean that this is the cardiac cycle, and if you look at the pulsatile flow, it followed this. We have a systole and a diastole in the blood flow. This is the pulsatile flow. Example, in arteries, as I mentioned, it could be normal in some veins close to the heart. You will see this when it comes to the, for example, the subclavian, the jugular veins. Okay, they are pulsatile. The IVC close to the heart, meaning the IVC that is in the area of the liver. If you go scan the liver, IVC near to the liver, and you put the sample volume there, you'll see that it's pulsatile. So again, veins close to the heart are pulsatile, and this is a normal phenomenon. Arteries, some veins, especially those near to the heart, and also in some pathologies, like in systemic veins, in some conditions, like some pathologies, like congestive heart failure, tricuspid valve disease, overhydration. We have several other factors, especially in the cardiac components, cardiac conditions that are ending by pulsatile in systemic veins, pulsatile flow in the systemic veins. So this is the pulsatile flow again, mainly in arteries, but you can see it in some veins normally or in other veins in a pathological state. The second form of blood flow is the phasic flow. Phasic flow, usually we see it in veins and is related to the respiratory cycle. So opposite to the pulsatile flow, We mentioned pulsatile flow is an arteries and related to the cardiac cycle. Physic flow is related to mainly in veins and is related mainly to the respiratory cycle. This is expressing why in some old terminology they call it the respirophasic. Respirophasic because it's related to the respiration. So physic flow or respirophasic flow is related mainly to the respiratory cycle. Now somebody will tell me what is the respiratory cycle? We have inspiration and expiration, inhaling and exhaling. So this is the respiratory cycle. Example specifically in veins. A third type of blood flow is the steady flow. And steady flow is fairly constant velocity. It's not undulating higher or lower. It's not responding to the circulatory, to the cardiac cycle or to the respiratory cycle. It's a fairly constant flow. Do we have examples? Yes, if we have examples in everyday life, if you notice the water coming from the garden hose is a steady flow. This is just an example of how it looks like a steady flow. It's not increasing or decreasing velocities. Uh, but in our body, do we have this? It might happen occasionally. If you ask the patient to cease, or the person can cease the respiratory cycle for a while, look at the veins. The veins are having now the steady flow. So steady flow in systemic veins, you can see it if you ask the patient temporarily to see the respiration for a while. Okay, you can. This kind of flow in the veins is called the steady flow. Do we have another example? Yes, we have it in the capillaries. Capillaries in our body, they are having the type of steady flow. What is this steady flow in the capillaries? Because arterial blood, we know that arterial blood is having pulsatile pattern or pulsatile form. But as the blood is going close to the capillaries, meaning that it's going in the branches and branches and branches till the end, that close to the arterioles and into the capillaries, it loses this pulsatility. The pulsatility that was in the arterial flow, it will be lost. What happened now? The capillaries will have a steady flow. Why is this important? Yes, because it's important for the exchange of gases, of carbon dioxide and oxygen, exchange of nutrients, exchange of water, exchange of waste products. All this, they need the capillary flow to be a slower velocity and a steady flow that can help this transport, the transport of gases, nutrients, waste products, all this between the blood and the tissues. And then the blood's getting into the venous side, and now it will be in the territory where it's under the effect of the respiratory cycle, and in the veins we have what we call the physic flow. Now, as we finish the study of the forms of blood flow, we need to study what are the energies that are responsible for the flow. The blood flow, it needs energy. What are these energies? Before we talk about the energies in hemodynamics, we need to know something about energies in general in the universe. There is one of the famous law of energy is called the law of energy conservation. We need to know this because it's important for us when discussing the hemodynamics. What is this law of energy conservation says? It says that energy can neither be created nor destroyed. It only converts from one form to another form, meaning that we have never have a condition that's called energy dissipated or energy vanished. No, energy is converted from one type or one form to another form. Okay, so this is one thing that we need to know because we're gonna have this in discussing the other forms of flow of energy that we're going to discuss in a moment. This means that system always the system means that any system of flow or metal or any kind of material, call it that system, it always has the same amount of energy unless it's added from the outside. Usually addition here is between a material that convert to energy. And this is something that is not important for us now, but energies can be added if some of the material is converted to energy. For example, burning wood, it adds thermal energy. So material convert to energy, all right? Now we come to the energies in hemodynamics. Okay, we finished the universal discussion of energies and the law of energy conservation. We need to come to the energies in hemodynamics. Okay, so if you want to understand the flow of blood from one point to another, it happens if you have a point A, for example, is having a higher energy compared to point B. So the blood moves from point A to point B. The movement it necessitates or should have a difference in the energy. We call it this energy gradient. So there must be an energy gradient between 2 points so that the blood flows from one point to another. The main type of energy is the pressure energy, as we're going to discuss in a moment. And that's why sometimes this energy gradient is expressed as pressure gradient, because the pressure is the main kind of energy or the type of energy that is discussed. That's why if we talk about pressure gradient, it's not that accurate, but it is practical to use. Okay, total energy is in any spot is the balance between the acquired energies and the lost energies, meaning that at any spot of time, any spot of tissue, any spot of blood vessel, there is a balance between the acquired energies and the lost energies, and the balance is more to the acquired energy, so the blood is moving. Okay, so the more the energy acquired, we have more fluid, more energy gradient. If we have loss of energies, we have energy gradient is going to be lost. So discussing the acquired energies, we have something to understand that we have a total acquired blood energy at a specific location is the sum of these three energies. So the total energy is not only one. We have the pressure energy, we have the kinetic energy, and we have the gravitational energies. All right? Come to the pressure energy. Pressure energy is actually derived from the cardiac muscle contractions. Okay, so it is any kind of pressure is a stored energy. Where this stored energy coming from in the hemodynamics is from the cardiac cycle, the cardiac systole. Cardiac cycle, we have systole and diastole. During the systole, this is the action of the heart that is delivering this pressure energy to the blood. And this pressure energy now is responsible mainly for the blood movement along the whole arterial and part of the venous circulation that depends on this cardiac contraction. So we have here pressure energy is obtained from what? From the myocardial contraction of the left ventricle, mainly for the systemic circulation, or the right ventricle for the pulmonary circulation. So ventricular contraction is the source of this pressure energy. Pressure gradient is between 2 points. For example, if I'm looking at the aorta, for example, the proximal aorta and distal aorta. Proximal aorta, if you have the pressure energy here is higher than the distal aorta, this will make the blood flow from the proximal to the distal. So pressure energy or pressure gradient is important for the travel of blood from proximal to distal aorta. The second kind of energy is kinetic energy. And kinetic energy is again it's a potential energy. It's a stored energy, same like the pressure energy. Okay, and it's derived from where? It's derived from the pressure energy. So kinetic energy is taking out from the pressure energy. It doesn't come from zero. It has a source. What is the source of this kinetic energy? Is taken or subtracted from the pressure energy. So kinetic energy and pressure energy can be interconverted. Yes. So that total energy remains unchanged. We might have pressure converted to kinetic or kinetic converted to the pressure. So these two energies, potential energies, they are interconvertible. Is related to the object's mass. This is how much amount of kinetic energy is obtained from the pressure energy. It depends on two things: how much is the mass of a movement and how much is the speed. If we assume this in daily life discussions, and now we can apply it to the blood. For example, if we have two vehicles, one is the weight is higher than the other, so but they are both having the same speed. For example, a little car and a truck. Okay, which one is having more kinetic energy? The truck. Though both are having the same speed, but the truck will have a higher energy, high kinetic energy. Somebody will say, how come? If you put a wall or whatever in front of both, the little vehicle cannot destroy this wall or cannot go through it, but the truck can destroy this little wall and continue moving. But why? Because it's having a higher kinetic energy. So it's related to the mass. Second thing is related to the speed. Imagine that we have two trucks, the same size, the same mass, but one of them is moving very slow speed and the other one is having a higher speed. Which one can go through this wall? The one that's having a higher speed. So again, the kinetic energy is related to the mass and speed. This is a general rule. When we come to our blood, the mass is the same. We mentioned earlier what is the mass, or the density of the blood is the same, right? So the mass is the same. But the speed is variable. The velocity is variable. We might have systolic and have diastolic. That's why, for example, a higher speed in, as we'll see later on in the stenotic area, that is having a higher speed of blood or high velocity of blood in that stenotic area, it requires a lot of kinetic energy, and this is taken from the pressure energy. So again, kinetic energy is related to the mass and the speed, and if I'm having a higher speed, higher velocity, requires more kinetic energy. Where is this coming from? From the pressure energy. Okay, again, we mentioned here that the pressure energy and kinetic energies are interconvertible. Third kind of energy is the gravitational energy. Gravitational energy, again, is acquired. It's a potential energy that is acquired or stored in any object that is elevated above the zero level, which is for the floor, for the gravity, for example. Okay, assuming that you have any object in your hand and you put it high up, like 4 feet above the ground, and another one is 1 foot above the ground. Which one will get a higher gravitational energy? The one that is the higher level away from the gravity, okay, taking more distance, higher elevated, this will acquire more gravitational energy. This gravitational energy, again, is a stored energy in this object. This is the energy that is forcing this object to move down if you release it. So again, the higher the gravitational energy, it comes from a higher level away from the gravity. And we'll see this later on when discussing the hydrostatics or the hemostatics, hydrostatic pressures in the effect on the arteria and in the venous system. Now we come to the energy losses. We mentioned earlier that the balance between the energy gain or the acquired energies and the lost energies, this will be the balance that is or represent the amount of energy that is present in a particular spot for the blood. So as the blood is moving, it loses energy. Again, as we mentioned earlier, the energy conservation, okay? Energy does not dissipate. Energy is not destroyed. So if I say loss, it's not really loss. It's converted to some other energy. That's it. So when I say energy losses, it's energy converted to some other energy that is not now, not pressure, not kinetic. Not pressure, not kinetic, not gravitational. It's converted to some other energy. And this is usually the thermal energy or the heat energy. So when I say energy losses, I'm converting, or not me, I mean the blood is converting its energy to another kind of energy, all right? So the energy losses, again, it happen when you have movement. So they don't come energy loss by when the blood is stationary. It happens when the blood is moving. What are these energy losses? We have frictional loss, we have viscous loss, and we have inertial loss. Again, we have 3 losses: frictional, viscous, and inertial loss. Okay, when you come to the friction, you can experience this if you rub your hand together in a cold day. You can feel the heat. There is some warming that happen in the palms because you put your hands friction or rubbing your hands together. This friction will create heat. Meaning what? Is the this kinetic energy in the hand is converted to another energy, which is heat. So now we are losing energy. We are not losing energy, we are converting energy from one type of energy to another, the kinetic energy to heat energy. So in the circulation, this is when the blood is sliding or rubbing against the intima of the vessel, this is kind of friction loss. What is the intima? This is the very inner layer of the blood vessels, arteries or veins. The very inner layer is called the tunica intima. So this tunica intima it basically is very smooth, very slippery, but still it has some friction loss or acquired some frictional loss. So there is conversion of one form of energy into heat. This is again, this explains why the law of energy conservation. Okay, we don't lose energy; we just convert it to heat. Another kind of energy loss is the viscous loss, and the viscosity, as we mentioned earlier, viscosity is given this Greek letter eta. Okay, this it looks like letter N, but it has more down end. The end of it goes a little bit more down. So this is the eta. Eta is the viscosity. Okay, again the unit is pOAS. We mentioned this area. It's the thickness or the stickiness of fluid. Of course, when we talk about the blood, it's the viscosity of the blood. It's related to what? The viscosity of the blood is related to how much water component in the blood. For example, if you have higher viscosity of the blood, like somebody is dehydrated or somebody is having a problem called polycythemia, for example, this is excessive amount of red blood cells, meaning that the amount component or the amount of water is less than the cellular component. This will give it more viscosity. So again, dehydration, it increases the viscosity, okay? And the blood is thick and becomes sticky to each other, and it's not easy to move. That's why it loses some energy, or energy is converted to heat to proceed to move this blood. Another condition, when we have a lower viscosity of the blood happen when we have a watery, for example, you are overhydrated, or you are your hydration is good, your blood is thin, better than the viscous blood. As the fluid thickens, viscous energy loss is increasing. Okay, increasing hematocrit, like we mentioned earlier, that is the thick blood, like polycythemia and erythrocytosis. These cause the increased blood viscosity. Anemia, or in other words, hydration or overhydration, this will make the blood thinner. Inertial losses. Inertial losses, we talk about inertial loss means what is the inertia is resistance to change the status, right? It's related to the tendency of an object to resist changes in its velocity or status. Objects at rest tend to stay at rest. Objects are in movement, they tend to continue in movement. So the status is what is the velocity? Zero velocity, this is at rest. Higher velocity, it's continued the same high velocity. Lower velocity, it tends to have the same lower velocity. So this is the inertia. It's a condition or a tendency in any object to persist or to continue the same status as it is. Inertial loss occurs during events of velocity changes, like what? Pulsatile flow, for example, both acceleration and deceleration, meaning that there is a velocity increases and then decrease. This pulsatile flow is losing energy through the inertia. Physic flow, the same story. The blood is moving faster, returning to the heart, faster and then lower, faster velocity and then lower velocity. This change of blood velocities in the veins is losing energy through the inertial losses. A segment of stenosis, because this is here, is applying changes in the velocity. The velocity is getting very high in a vessel in an area of narrowing, like stenotic area. So the high velocity is again another inertial loss. So now this is the time to study the laws of hemodynamics. There are two main laws actually. These are called the Ohms Law and Poiseuille's Law. Originally they are controlling the hydrodynamics, not hemodynamics, but they are applied for the field of hemodynamics too. These two laws are actually discussing the effect of some factors. Originally, we knew something about them. These are the delta P, the pressure gradient, the resistance to the flow, R, the vessel radius, and a radius is half of the diameter, so, and it's giving this little r. This is a sign of the radius, not, we need to make sure that it's different from the big R or the capital R, which is for the resistance. Also, we have the velocity, V, the length of the vessel or the segment of the vessel under study is L, and the viscosity, which is, we know that is giving this sign or letter eta, the Greek letter, and all of these have been studied by these two persons or these two scientists, and Poiseuille. So let's start by Ohm's law. Ohm's law is mainly studying the electricity, not the hemodynamics or the hydrodynamics. But this law actually is found to be applied also to the hydro and hemodynamics. So this law actually, in the original statement about it, is talking about the voltage, which is V voltage, the amount of electric current flow, which is I, they put it here, and the resistance to the electricity, which is R. So as we see here, we have the voltage, the amount of flow, the electric current flow, and the resistance to the electricity. And based on the work of Ohms, he found that this is these are actually the formulas that we can come out from this. We call it the Ohms triangle. Ohms triangle is talking about these three factors. And here we have V, the voltage equals what? V equals the current multiplied by the resistance. So this is I multiplied by R. Or we can come with another formula, which is the current, how much is the amount of electricity flowing in a wire. And they give it the letter I. I equals what? V divided by R. So I equals V divided by R. Or if I want to know how much is the resistance, I can get the voltage divided by the amount of electricity flowing in the current, and this is R equals V over I. So as we see here, we have these three formulas or three equations coming out. We can understand them from this Ohm's triangle. If we apply this to the hemodynamics, we come to another formula, which is very similar to the Ohm's law. So now come to the application of Ohm's triangle in the hemodynamics. And as seen, again, we have three factors, the same or similar factors to those for the electric current. We have here, instead of the voltage, we have the delta P, which is the pressure gradient. Instead of discussing about the flow of electricity, we have here the flow of blood, the amount or the volumetric flow of blood, which is Q. And also, instead of the resistance to the electricity, we have a resistance to the blood flow. So again, we have three factors, and all are included in this Ohm's triangle. We can apply this a little bit similar in another diagram here. And this diagram is having the same three factors, the delta P, the Q, and the R. But in this way, I think it could be easier to understand. We have the pressure gradient in one side, which is pushing the blood in this direction to flow forward. But in the other side, we have resistance to this flow, and we put it here in the other direction. So these two forces, or the delta P and the R, are opposing each other. The balance between them, the ratio between them, will determine how much of the Q. So I can understand that the Q equals what? Delta P over R. The balance between these two factors will determine how much blood flow in this segment. So if you come here, this is the middle equation here. Q, which is this one here, equals delta P over R. So Q equals delta P over R. But if you want to continue or to apply this to the rest of the Ohm's triangle, we have delta P here equals what? These two multiplied by each other, so Q multiplied by R, this will give me delta P. Also, Q mentioned this before, it equals delta P over R. And R, the resistance, equals delta P over Q. So as we see here, these are the three factors that are contributing together to form the Ohm's triangle in hemodynamics. So based on this Ohm's triangle or Ohm's law in the hemodynamics, we can understand the relationship between three factors: the pressure, the flow, and the resistance. So we have here three factors: pressure, which is the pressure gradient, the flow or the Q amount of blood, and the resistance. And again, these are the same equation or the same formula that we come up from here. So what are the things that we can understand? We can understand that pressure gradient, as we mentioned earlier, is the pressure difference between 2 points here, the pressure in point 1 and the pressure in point 2. If there is a difference, there is a pressure gradient. So delta P here actually is coming from these two pressures. R is the resistance, and we know that this is a long story. It could, but in short, it could be what we call the peripheral vasodilation. This is one factor of the resistance, or the vasoconstriction, vasodilation of the arterioles. And another factor is if there is, on the way, there is a segment of stenosis. Again, the presence of a segment of stenosis is applying pressure to the flow of blood. So we have two factors that are used in this R. So when you come here to the application of this formula in hemodynamics, we can come up with this conclusion. So if I'm increasing the flow of increasing the delta P, okay, this will lead to more flow of blood. So the flow of blood increases with what? With, if I'm increasing the delta P or lower the resistance, right? So increasing the pressure gradient or lowering the resistance, anyway of these, they will lead to the increase of blood flow. Now we come to the second law, which is Poiseuille's law. Poiseuille was a French scientist, and his work was focusing on how much what are the factors that are contributing to end up by the resistance to the flow. And applying this Poiseuille's law to the blood, we have here the hemodynamics factor, okay, and we come to, or we can understand that the resistance of blood flow is related to three main factors in the flow of blood. First is the radius. The radius is what? It's the half of the diameter. If this is the cross-sectional area, from here to here is the radius. So radius is half of the diameter, right? So he found that if lowering the diameter, meaning the vessel or the blood vessel gets narrower, we have a higher resistance. So again, the first factor discussed is the radius, and we found that lowering the radius increased the resistance. Second factor that was found is the length of the segment of blood vessel that the blood should travel from here to here. So we have this length of vessel. If I'm having a lower length, means that we have less resistance. If the length is longer, they found that the resistance is getting higher. So increasing the length increase the resistance, okay? And the third factor is the viscosity, and the viscosity is giving this letter. We know this. It's called eta. Eta is a Greek letter. Is used to as a sign or a symbol of viscosity, and viscosity is what? It's the thickness of blood. Thickness of blood, here we might have a higher thickness if we have the hematocrit value is high. Hematocrit, what is the hematocrit again? Is the number of red blood cells or the percentage of red blood cells within the blood. So if I'm having more number of red blood cells, means this blood is more viscous. If I'm having a lower number of red blood cells, for example, in anemia, we will find that this blood is less viscous. So again, higher viscosity, higher resistance. So again, we have here these three factors: the radius, the length, and the viscosity. So applying the resistance in the work of Poiseuille to hemodynamics, we have this formula, and this formula, it says what? Resistance equal number 8 multiplied by the length of the vessel, multiplied by the viscosity of the blood, divided by pi, which is 3.14, multiplied by r, the radius, raised to the fourth power. This formula is concluded, or one of the work results of Mr. Poiseuille. And we apply this in hemodynamics. We need to understand these factors again. R is the resistance, big R, high case R. L is the length of the vessel under study. Eta, which is the viscosity, and viscosity is the thickness of the blood. So if you have somebody who's having a condition, for example, called polycythemia, which is increased number of red blood cells in the blood, this will increase the hematocrit. The hematocrit is increased. What happened? The viscosity will be thicker. The blood will get thicker when having increased viscosity. What happened to the later after that? Increasing the viscosity will lead to what? Increasing the resistance. So the resistance increase. This will lead to what? Lower Q and velocity of the blood. This is thing that we need to know about this condition, which is the polycythemia, or with high hematocrit. That is not good because actually it will lower the amount of blood flow and the velocity of the blood. This is the thickness of the blood is affecting negatively the flow of blood. Another factor, which is pi. Pi is 3.14, so it's a constant number. So just a quick word here. In this formula, we have two numbers which are constant. They are not variable. Number 8 is a constant, and pi also is constant at 3.14. So when you come to the pi, it's constant 3.14. It's not a variable, it's a constant number. And then we come to the r, and we have to hear a little talk about r, the radius of the vessel. Based on the work of Poiseuille, he found that the radius of the blood vessel, as it shortens or the blood vessel gets narrower, there is a big impact on the resistance. And he found that this relationship is actually, it will be constant if we have r raised to the fourth power. So it means that r is multiplied by itself 4 times. We need here to mention that is r multiplied by r multiplied by r multiplied by r. It's not r times 4. It's a different story, guys. We need to understand this. It's not r times 4. No, it's r times r times r times r. Okay, so we need to understand this fact. So radius here is multiplied by itself 4 times. Okay, this will get an impact over the big impact actually over the resistance. Okay, and that's why the radius of the blood vessel is the main factor that will contribute in applying to the resistance, the total resistance. Why? Because it's raised to the fourth power. So to emphasize the relationship between the radius and the resistance, we need to understand it very well. So the radius here, this is the half of the diameter of the blood vessel. If it happened that I get this radius double, so I'm having the radius here double, it was 1 making 2. So what will happen to the value of the radius here? Raised to the fourth power, the value here will be what? 2 times 2 times 2 times 2 means that is 16. So if I'm having the number here, instead of r raised to the fourth power, I put number 16. What happened to the resistance? Resistance will drop 16 times, meaning that is a very low resistance. The resistance drops 16 times if I'm having the radius of the vessel just doubling the radius. And this will give us an idea why, if somebody is having, for example, a segment of a stenosis or plaque, doing the surgery and removing the plaque or putting a stent will tremendously affect the resistance, and this will lower the resistance as much as possible so that the blood flow can go as much as we can to the area of its destination. For example, the organ that is, for example, the brain or the heart, or whatever the organ that is having suffering from this narrowing of its blood supply because of the plaque. So now we come to something that we need to understand here. If I have, for example, this is the Ohms law. We know this originally. Delta P equals Q times R. Okay, delta P equals Q times R. Okay, delta P Q R, delta P Q R. Okay, so this is the formula that is by Ohm. Now we know that based on the work of Poiseuille for the resistance, he found that these factors, that all these factors together, are contributing to the resistance. So if we have a chance that we might get this radius here, and we have substituting all of this together, and substitute them to the R here, because this R is equal to this. So I substitute in the work of I substitute R by these factors. What happened? So if I get these factors here, to substitute R, I come up with the formula, which is the end formula, or the last formula that we need to understand about Poisson. What is this formula? Okay, as we see here, we have delta P, which is this one, equals Q. Okay, if I have here Q, put it in green, because here. So I keep it the same, Q. Delta P here is delta P, so delta P here is the same. Q is the same, okay? What happens? I replace R by these factors, okay? So what happens now? These are, I multiply R here, okay? I will put them over here. So now I can understand this is the formula of Poiseuille together with the formula of Ohm. So this is the last formula, and this is the thing that we need to understand. This is called the Poiseuille's law. Poiseuille's law equals what? Delta P multiplied by R by Q, and then R is substituted by this factor. So we need to memorize them. 8 times L times eta, 8L eta, 8L eta, divided by pi R to the fourth power. 8L eta divided by pi R to the fourth power. Again, 8L eta divided by pi R to the fourth power. So all these factors are considered as the resistance multiplied by Q, that will give me delta P. All right. So in other words, I can reformulate it, because in mathematics I can reformulate the formula. So I can put here Q, which is the practical application of the Q. Okay, Q is what? Q is, again, Q is the volume of blood flow, equals what? Okay, delta P, the driving force, multiplied by pi, multiplied by R to the raised fourth for the raised fourth power, divided by 8 times L times eta. Okay, these factors, actually, this is the formula that will help us to understand what we can do if somebody is having deficiency of blood flow to some area. So if you have somebody who's having deficiency of blood flow to an area, this will help. So increasing the pressure gradient, increasing the force of the heart. Okay, this is constant. I dilate the vessel if there is a segment, or I can apply some vasodilators, which are the drugs, medications, okay? Or I put a stent, will dilate the vessel itself. Divide by 8, it's a constant. Divide by L, this is the length of the blood vessel, and divide by eta, which is the viscosity. If I'm lowering the viscosity, I will increase the flow. For example, somebody who's having concentrated blood, I ask them, okay, drink a lot of water to make diluted blood. So we have here some notes. Again, these are to apply practically in the field of hemodynamics, which are based on the Poiseuille's law. If the pressure difference increase, the flow rate will increase. Delta P increase, I'm getting flow rate increase. If the radius is doubled, what happened? Okay, the blood flow will increase to 16 times. Radius doubled means times 2, but here I put it to the fourth power. So it's not only times 2, it's times 2 times 2 times 2 times 2. If I'm double the radius of the vessel for some reason or another, I can do that. What happened to the amount of blood flow will increase because they are now directly related. Okay, so the Q of blood or the amount of blood will increase 16 times. Okay, so this is another factor to mention. The length of the blood vessel, actually, I cannot change it because this is anatomy. I cannot increase or decrease the amount or the length of the blood vessel. This is anatomy. I can do nothing about it, but it's a factor if we can do it. Okay, and then the viscosity, and this how the viscosity will help. If I'm lowering the viscosity, the amount of blood will increase. How can I lower the viscosity? A simple thing: ask the patient to drink water, as many cups of water as they can. So this will help to dilute the blood, and this will increase the amount of blood flow. So after finishing the laws that will help us understand the hemodynamics of blood in our vessels, we come to these patterns of blood flow. The patterns of blood flow, we have two main patterns. Okay, we have the laminar flow and the turbulent flow. Laminar flow is the very well organized. They come in layers. The blood flow is traveling in layers and parallel to each other, and they are respecting the traffic law, so they don't cross each other. They don't have any problem. And this is the laminar flow. And actually, laminar flow, we have two types. The blood flow, when you have the velocities are almost in the same velocity, or parabolic flow, when we have the velocities in the near to the peripheral blood vessel, they are a little lower because of the friction. So we have here the parabolic flow. And we have the other factor, or the other pattern of flow, which is the turbulent flow. And this is the chaotic or disturbed flow or highly disturbed flow. These two factors, or two types of patterns of blood flow, are like understood if we understand something called the Reynolds number. Reynolds number, if we have a Reynolds number less than 1500, this will be on the side of laminar flow. If the Reynolds number is more than 2000 to 2000 and higher, this will it belongs to the turbulent flow. So Reynolds number, as we mentioned earlier, is it has two main numbers to memorize: 1500 and 2000. 1500 means that 1500 or less, this it goes to the laminar flow. More than 2000, it goes to the turbulent flow. How about the numbers in between? For example, 1700 or 1800. Okay, this will end up by what kind of flow? Is it laminar? No. Is it turbulent? No. It's called disturbed flow. Some people call it the gray zone flow or the disturbed flow. It's not completely laminar. It's no longer laminar because the streamlines are disturbed, they are shaking, they are little disturbed, but in the meantime they are a little altered, but in the meantime they are not yet called turbulent. So this status is called the disturbed flow. So we mentioned the Reynolds number. What is this Reynolds number? It depends on what? It depends on diameter of the vessel. The wider the vessel, the higher the turbulence, the higher the number. The fluid or the blood velocity. Higher velocity increases the chances to get turbulent flow. Higher density, as we mentioned earlier, the blood is higher density than water. So blood is more supposed to have turbulence compared to water, okay, density. And the fluid viscosity, and the viscosity here, a higher viscosity will lower the turbulence. So the first three factors, they are going in a direct relationship to the Reynolds number. And the last one, the viscosity, is in the opposite or the inversely related. Okay, this is the Reynolds equation. Reynolds number equals what? The velocity, okay, times the diameter, the velocity of the blood, times the diameter of the blood vessel, times the density of the blood. All are divided by the viscosity, which is the thickness of the blood. So this is the formula of, we need to know what are the factors, okay? We don't need to know the numbers or whatever, just know the equation here, the last number here, which is the Reynolds number, but we need to know the factors, see what are increasing, what are decreasing the Reynolds number. So for example, if I'm having a higher velocity, I'm going to give it a higher chances to get turbulence. Wider diameter, I'll get higher chances to get turbulence. Higher density, I'm getting higher chances to get turbulence. Higher viscosity will lower the chances to get turbulent flow. So now we come to these main types of flow, the laminar and the turbulent flow. So laminar flow, when you have the Reynolds number 1500 or less, the flow streamlines are parallel layers. They are parallel, they are not disturbed. They go in equal distance from each other, so they are parallel, they are organized, very well organized. Okay, it's a silent flow. What does it mean silent? It doesn't produce any noise. So there is no noise, no murmurs, no thrills, no nothing. It's a silent flow. This is a very quiet silent flow. It's found in normal physiologic status, for example, normal arteries, normal veins. Both are having a laminar flow. It shows, if you come to the Doppler spectral waveform, it shows narrow spectrum. So there is clear window, there's clear window, there is narrow range of velocities. The range of velocities is close, and in this, if you apply color, you'll see that the color is not having any signs of turbulence, like no blue within the red or no red within the blue. It's with the same color, right? So it has two patterns we mentioned earlier, that we have the plug or parabolic flow. So these are the two patterns that we mentioned. We have plug flow and parabolic flow. What is the difference? The difference is in the rubbing or the friction, the layers of blood that are close to the vessel wall, because of some friction, they will lag behind. So what happens? Those in the center, they are moving fast, the same velocity. Those in the periphery, because of the friction with the blood vessel wall, what happens? They lag behind. So what happens here? We get what we call this is the parabolic flow. Parabolic flow is again related to it's a laminar flow, but it's related to the friction that happens in the periphery of the blood vessel. Now we come to the turbulent flow. Turbulent flow, it has many other names, okay, like chaotic flow, hurricane-like flow, rotational flow, swirling flow, eddy current flow, or vortex flow. All these are describing this chaotic, irregular pattern of blood flow. This is called the turbulent flow. Velocities and directions of blood are rapidly variable from one instant to another and from one location to another. So you can't tell that this location is having forward and this location has backward flow. They are different flows in different locations and different velocities in different locations. All right. So streamlines are obliterated or intersected. As you see here, they are intersecting each other. They are obliterated. The streamlines are no longer laminar. Okay, and at the end, the forward net flow is still maintained. So the blood is moving forward, but still has some turbulence on its pattern. Turbulent flow is associated with what? As we mentioned earlier, okay, it's related to the Reynolds number. What are the outcome if I'm having turbulent flow? How can we tell? What are the consequences of turbulent flow? It could be audible consequences like a bruit, or sometimes called the murmur, or it could be palpable, like put your hand over a turbulent flow vessel. You will feel that there is thrill, there is some vibrations in the vessel, okay, and this is called the turbulent flow thrill. Doppler spectrum, we have Doppler spectrum waveform. What we will get? You will get spectral broadening and filling of the window. And if you go color, what happens? You get what we call the mosaic pattern. You get blue within the red or red within the blue, or different colors. But if you are using the variance map, you will get another color, which is the green or purple. So it depends on the map you are using. If you are using the variance map, turbulent flow will show as a different color, completely not red or blue. You will get either green or purple color. So do we have some examples of turbulent flow in our body? Yes, we have. We have examples that are physiological examples, and others are pathological. Physiological means they happen natural. So do we have natural turbulence in our body? Yes. And the very famous example everybody knows is what we call the flow separation or boundary layer separation that happen in the carotid bulb. Carotid bulb is a famous example of the physiological turbulent flow. But still we have pathological, means that somebody will ask you, is all the time if you have turbulent flow, it means that there is a pathology there? No. Sometimes it happens naturally. So anyway, so we go to the pathological. Pathological like what? Arterial stenosis, post-stenotic turbulence. Everybody is familiar with this term. Post-stenotic turbulence is pathological because there is a stenosis. Also, if there is some heart valve disease, it might end up by some turbulence or excessive turbulence within the flow of blood in the heart. Thank you, and I hope that was beneficial, and see you in the rest of the Doppler lectures.